Record. Okay, so let's see. We just had a new visitor. Lorena has joined the house. Cool. Good morning. Welcome. So again, if you have particular questions you want to take a look at today, just put them in the chat and I'll look through them. Just a reminder of where we left off. So we had the derivative with respect to x of the natural log of x is 1 over x, and we used implicit differentiation to come up with that. And then we found that the derivative with respect to x of e to the x is itself e to the x. And the only other function that happens for is the derivative of 0 is 0. Otherwise, a function is not a derivative of itself. Trig functions are close, right? The sine and cosine bounce back and forth between each other. So hopefully you read the book and you took a look at other functions in there that they took derivatives of. For example, what if I have log base 10 of x? What's its derivative look like? And in the homework, I had a note that said, hey, when you take this derivative, think about a different base. And the change of base rule for logarithm says you can change to any base you want, pick your new base, whatever it is. I'm going to pick e as my base, and then just divide by the old log of the old base. So if we continue this derivative through now, we've got this divide by the natural log of 10. So that's a constant multiple. So that just pops out as 1 over natural log of 10 times the derivative of the natural log. And the derivative of the natural log is 1 over x. So we get 1 over natural log of 10 times 1 over x, which you could just call 1 over natural log of 10 times x. And it doesn't really matter what that base was there. So kind of in general, if we take the derivative with respect to x of log of any base b, because of the change of base formula, that's going to end up being 1 over the natural log of the old base times x. And reminder, log base 10 is often written as just log of x. And then there's a similar rule for any base besides e to the x, and hopefully you look this up. So if I wanted to take the derivative with respect to x, oops, premature on my x there, of any base b, there's a change of base, or you can look at it as a change of variables that can be rewritten as e to the power x times the natural log of b. And that's, this formula here is related to the change of base formula for logarithms. And if we take the derivative of that, derivative of e to whatever is e to the whatever. So I get e to the x natural log of b times the derivative of the exponent, and the derivative of x times something that's linear is just that thing. So natural log of b. And then this monkey right here, think about the log rule where powers become multiples. So this part right here can also be written as e to the power natural log of b to the x. We still have that natural log of b multiple hanging on. And the natural log, e to the power natural log cancels their inverse functions. So this becomes the natural log of b times b to the x. So we have this more general, any exponential base, we have to multiply by the natural log of b to adjust. All right, one more example, and then I'll start going over your questions. There's another cool idea called logarithmic differentiation. And so I would use that for something like y equals 1 plus x to the power x. And if x is greater than 0, then this is a continuous function there. And to take the derivative of this, I have a problem because there's kind of two rules I got to think about. And the rules that are conflicting here are the power rule. So if you have x to the power b and you take its derivative, then you get b times x to the b minus 1, right? Multiply by the power, reduce it by 1. On the other hand, we have x in the power, and so that means, hey, do we apply the power rule, where if we have something like b to the x, then the answer is the natural log of b times b to the x. Which rule do we use? It turns out both of them are involved, and the way to get at that is to just clean this up by taking the natural log of each side. So this was some of your homework, and I said you would need to read the book about this. So hopefully you did, and this went all right. Once I take the natural log out of both sides, I can pull the power out. So now I get x times the natural log of 1 plus x. On the other side, I just have the natural log of y, and now I can implicitly differentiate on each side. So now I can say, okay, what's the derivative with respect to x of this side? That's got to be equal to the derivative on this side, because the original things were equal. So here I have the natural log of y, and here I have x, natural log of 1 plus x. On the left side, the derivative of the natural log of something is just 1 over that thing. And then the chain rule says if y is a function of x, which it is up there, then I have to multiply by y prime. That's the derivative on the left side. On the right side, I have to apply the product rule, which says take the derivative of the first function, derivative of x is 1, times the other function. Add that to the first function, x, times the derivative of the other function. And the derivative of a natural log is 1 over 1 plus x times the derivative of the inside, and the derivative of 1 plus x is just 1. So we do have to double check the chain rule there because there's more than just an x inside the function. So this is a chain rule along with the product rule. So cleaning that up, what do we get? We've got just the natural log of x, or 1 plus x, excuse me. And then we have plus x over 1 plus x. In the denominator, we want the derivative y prime, so we have to multiply both sides by y to get that y out of the denominator, and this right here is y. So I need to multiply that over to the other side. So let's see, scroll down a little. Switch color, there we go. So now y prime is going to be equal to multiplying y over to this side, and y is 1 plus x to the power x, times everything on the other side, right, all of this. So next I'm going to distribute that through. So then I get, I'm going to write it as natural log of 1 plus x times 1 plus x to the power x plus x over 1 plus x times 1 plus x to the power x. Now here, I hope you notice that there's a 1 plus x to the power 1 in the bottom and a 1 plus x to the power x in the top. So I'm going to use the quotient rule for powers on that. So I still have this first term, natural log of 1 plus x times 1 plus x, the power x. And then over here, I have plus x times 1 plus x to the power x minus 1. And what you end up with is that conflict I saw earlier where, hey, do we apply the power rule here, or do we apply the exponential rule? And it turns out they're both here. So the first one I wrote is pretty much this right here, right? My base is 1 plus x, so I have the natural log of 1 plus the base, or a natural log of the base, times that exponential function. And then I have plus, the power used to be x, but we brought the power down and reduced the power by 1. So the cool thing about this function is it's both an exponential function and kind of like a polynomial function in a weird way wrapped into one, and both rules end up getting kind of thrown together and added up. And there is what's called a generalized exponential power rule, or a generalized power rule, which is related to this. But I don't think we need a new formula because we can always use logarithms on each side. So you had a couple homework problems like that. All right, next.